Sir, good morning, sir.
Morning.
Yes, sir. Okay, sir. Sir, we can wait for some time, sir. The participant will join.
Yeah.
Okay,
Okay,
sir.
nice.
Thank you, sir.
Sir, shall we start, sir? Sir, you are not audible, sir.
Yes, sir, we can start.
Okay, sir. A very good morning to all the participants and warm welcome. Today is the third day for FDP. Today we have Professor Susanta Kumar Das, Dean Research, Gangadhar Meher University, Sambalpur. Sir, I extend my hearty welcome to you, sir.
Thank you, sir.
Professor Susanta Kumar Das, who is the Dean Research of Gangadhar Meher University, Sambalpur. He is also heading the School of Physics and coordinator of School of Electronic and Information Science in the same university. He has obtained his MTech degree from IIT Delhi and PhD degree from IIT Kharagpur. He held the postdoctoral scientist position for 6 years at Max Born Institute, Berlin, Germany. His research areas are development of high-end medical and industrial lasers, low cost and green battery, solar technology, electronics and instrumentation for cost-effective climate control, agriculture. So far, he has completed 8 PhD scholars and 4 scholars are pursuing PhD under his supervision. He also guided many MTech, BTech, MSc students for their project work. Almost all of his students are now well placed in faculty, scientist position in Odisha and other parts of India. Even they are working in abroad, like country like Germany, USA, Japan. He has published more than 120 research articles in the reputed international journals and conference proceedings. These papers have been cited by more than 1,500 scientists, researchers of India and abroad. His search index and I index are 18 and 24 respectively, which are at par to the leading scientists, researchers of the world. Recently, Professor Das played a lead role in establishing various modern laboratories like laser and photonic laboratory, green energy harvesting laboratory, agrophysics laboratory, etc. at GM University. As a coordinator of career development and placement cell, he has coordinated in placement more than 300 number of students for all stream of arts, science, and commerce through on-campus and off-campus interviews. Yeah, he has also worked in GM University as PG Council Chairman. This is an academic head position of university, which is next to Vice Chancellor. In this capacity, he has also played a significant role in updating the syllabus, teaching methodology, and assessment procedure. He is a recipient of prestigious award like IC Vidyasagar Award. Sir, we are really honored to have you as a resource person on day 3 in session 1. Sir, the session is yours.
Okay, thank you, sir. Dear participants, good morning to all of you. I believe it's audible to all of you. Give your comment in text. I can listen or I can see. Is it audible to all of you? Yes.
Yes, sir, it's audible, sir. You can proceed.
Fine. So, just before starting, let me tell you, this Gangadhar Meher University is a newly established university. It was earlier a college, and all the faculties which are now in this university have recruited in 2020 only. So within 5 years, we tried our best to give a best shape. So many responsibilities I had to take. So apart from continuing my regular activities. Okay. Anyway, so today my talk title, So without wasting much time, I'll go directly to the talk. So for that, let me share the screen. Uh, so, so this is the title of my talk. Can you see the screen? I believe yes.
Yes, sir. Yes, sir. I
Good.
can see the slides.
So before start, I would like to convey my gratitude and sincere thanks to the organizers for inviting me to this FDP program. Uh, I am working in different field. This is a part of one of this field. So let us go to the overview of the talk. Mostly, I'll give a introduction and motivation of this work. Then I will mostly deal with or discuss with about the compound semiconductors like zinc oxide, titanium dioxide, and the zinc orthotitanate, which is a mixed material of zinc oxide and titanides. All of them are very cost-effective material I have chosen, and various cost-effective methods we have adopted for doing the photocatalysis applications for water purification. And I am also an expert in instrumentation, electronic and optoelectronic instrument. So couple of example I'll show where I have developed various instrument for continuing my research. So to start with, let us see what is a photocatalysis. Photocatalysis is a term that can be divided into three parts. You can see photo, kata, and lysis. Photo means light. Catalysis, all of you know catalysis. It's an element that can hasten a reaction. And lysis means splitting, particularly splitting bigger molecule into smaller molecules. That type of application we are taking care of. So in presence of light and catalysis. One example of photocatalysis I can give you here, splitting of water. It is given in the below to its constituents like hydrogen and oxygen. You see, there is plenty of water available in the world, and one can go for splitting it to its constituent, like as I told you, hydrogen and oxygen. But being water is a very stable element, it's very difficult to split it. And that can be done in presence of some nanostructures like titanium dioxide or other semiconductor nanoparticles, but in presence of UV radiation. Sometimes other kind of radiation can also be given. I'll tell you later. And once you are splitting, you are getting very useful element like hydrogen, which is considered to be the green fuel, or the fuel of the next generation, fuel of the future, and oxygen, which is very vital for our livelihoods. So this reaction cannot take place without such photocatalysis process. So uh, to know the process, how it really takes place, here is a schematic diagram. Generally, splitting, this is a kind of redox reaction. So that's why in the definition I have mentioned redox reaction in presence of light and semiconductor nanoparticles. Semiconductor nanoparticles are catalyst here. Light is the photons. So you see, these reactions are very often called a redox reaction, means reduction and oxidation reaction. In this reaction, hydrogen, this valency actually reduced from +1 to 0, so it is a reduction reaction, and oxygen minus to 0, so this is oxidation reaction. So reduction and oxidation reduction together called as a redox reaction. And this type of reaction can easily take place in presence of various elements like you can see here, particularly electron and electron play a lot of role in this type of reaction. So what happened, the mechanism is given here. What happened when the light fall onto the semiconductor nanoparticles, then each photon energy is more than the band gap of the material, then electron hole pair generates. Then the electron react with the oxygen that is already present in the water, and it can form a radical oxygen, that is oxygen with a negative charge, and whole can mixed with water, and it can give us radical hydroxy element. These elements are very highly reactive, and they facilitate the this reaction, okay, which is otherwise almost impossible. Okay, there are several applications of this photocatalysis. For example, anti-fogging, air purification, antimicrobial activity, water splitting for green fuel generation, water purification, and self-cleaning. These are the various applications. Uh, in each and every field, there's a lot of research going on. And at this point of time, I'm mostly working with water purification and also started work in antimicrobial activity. So, but in today's talk, I'll be telling about the water purification aspects. Now, before going to that, these are the some view graphs of self-cleaning and sterilization of equipments. In the self-cleaning, you can see there will be all the water molecules and the dust particles that can come to the glass or mirror can be self-cleaned, and the sterilization can be done to various medical equipments. Also, it can be used for deodorization, antimicrobial water treatment, and dirt prevention. So there are several advantages of this process. Uh, it's not that this process can be used for those applications. So several other processes can be used, but the photocatalysis is a distinct advantage. It is very cheap, environmental friendly, and sustainable. So that's why the research on it is going on tremendously, and it is a very valuable research, as you can see from this slide. It's Japan is one of the country in the world, leading country of the world, which is generating the almost highest amount of revenue by the photocatalysis. You can see in 2025, this is crossing the $1 billion also. So, and mostly these two elements are getting used, titanium and zinc oxide. This is from a screenshot which shows about the importance of the market size or the value addition of this research. Now, the category of various applications, their revenue generation is like this. Mostly automobile and construction sector, they are dealing with self-cleaning, so that has the highest share. Then air purification, water purifications, it's also significant here. You can see. Now, coming to water pollution and need of the purification. You see, water of the water reservoir of Earth can get polluted in different way. For example, from the industry, various industry like textile industry, pharmaceutical industry, paper industry use huge amount of dyes, and these dyes in a small amount is well okay for the human body, but or the other aquatic animals or creatures. But when it is there in excess amount, it is very hazardous. And because this industry continuously trying to in various countries, they are releasing this contaminator, the waste of the industries to the water reservoir. So it is creating a serious environmental problem. So that, and it has the severe bad effect, as you can see. This is the human being, the effect that the human being that are facing. But as I told you, aquatic animals and other creatures also get affected by this. Okay. Now coming to the work of I like to start with photocatalytic dye decomposition using cost-effective zinc oxide nanoparticles. Probably many of you are new to this field, so let me tell you, zinc oxide is a material, compound semiconductors. It's a wide band gap semiconductor material. It's a direct band gap also. When it is a direct band gap, so its photon absorption capability is more. It has got large excitant band gap and good electrical conductivity, good chemical stability, and antibacterial activity. And there are several techniques that can be adopted, but here we are using ball milling or mechanical methods. So I'll be most, and also other cost-effective method like sol gel. So about those things I'll tell you in my subsequent slides. Now, so let me tell you the motivation behind this research. I started this research on this field around 12 or 13 years before. Earlier, actually, my actually core field is my degree is in photonics, particularly in ultra fast laser. The laser, you know, are generally used in all field, including the medical and industry. So I was mostly dealing with development, design and development of lasers. My PhD at IIT Khodagpur is in that field, and my postdoc also in that field. But at the same time, at Germany, I started working development of various sophisticated materials using the laser, along with development of the lasers itself. So when I started growing the materials with the lasers, then we started doing the applications also. Then this photocatalysis is one of the applications that I started at Germany. Then after coming back, I continued that. So when I found in the literature in that time that I found that most of the research going on in the zinc oxide with the SCS or reagent type of zinc oxides, which are very highly pure uh, materials, and they are expensive also. Then I found that on the other hand, I found that there are laboratory grade zinc oxides are available, which are very cheap in nature. You can see the price for the laboratory grade zinc oxide. It's for 500 gram you can get at 500 rupees. So I started doing that work with the low cost zinc oxide. And for that, first thing that I had to do is to develop a photocatalysis reactor. If you go for searching a reactor, then it will be coming in few thousands and in lakhs. But in the beginning, because I joined in a after coming from Germany, I joined at a university called KIT University at Bhubaneswar, which was in a very low level university at that time in 2013. So almost no funding were there, no infrastructure were there. That was a private, and still it's a private university. It's a now very big university, having 25,000 student capacity. So at that time, it was a small university, and almost these things we had started from our own pockets at that time. So in a very low cost, I developed the reactor. It consists of a magnetic stirrer and a UV light source, which was of 6 watt, and its wavelength was 365 nanometer. I tried different distance configuration, and I found that in this power level, 10 centimeter was optimum. And then we just purchased the zinc oxide from NICE, and we just gone for ball milling or grinding them. Then we started the experiment. And this is the standard concentration that one has to go for to test the materials. The concentration of the we tested with the methylene blue first with the molar concentration 2.5 into 10 to the minus 5, and this is the typical zinc oxide that has been used with the SCS and reagent grade. So that's the amount we had taken, and we had done the experiment. And while doing this experiment, when anybody do the experiment, one has to do the comparison with the standard materials also, nanomaterials, that is called P25 or Dugusa P25. that is titanium dioxide nanoparticles. The one has to compare with that. So we did also that. Now we did the experiment also with the visible light reactor. That also we have developed, particularly myself, my PhD scholar developed these things. In this time, we have taken little bit bigger setup, and we have taken the halogen lamp with power of 500 watt wavelength. Halogen lamp generally give a broad wavelength range, and this is the wavelength that you can see that we have taken from our spectrometer, which wavelength range is within 450 to 860 nanometers. So it's a visible kind of radiation, so one can see. And we have also done the experiment directly with the under the sun, so particularly under natural solar light exposure. So we did that also. So these are all about the experimental part. Now this is while going for this material preparation, we have also gone for various characterization and measurement techniques like XRD, FPSCM, UV visible spectrophotometer for observance and transmittance study. All these things we have also done. But for these things, I had to collaborate with Niger, which is located at very nearby our institute at Bhubaneswar itself. And also, I very often frequently access the facility of IIT Kharagpur, which was just overnight journey from my institute. So now at KIT and here also we have lot of facility here. Now the XRD analysis. Now in the subsequent things, I'll mostly deal with the results. The important results I'll discuss, and many things are similar, so I'll try to skip them. So you see, we had gone for XRD and we found that there is almost no peak changes. But we have done the Schwerer analysis and we found that the crystalline structures were much reduced, and that was also verified through TEM. This is advanced study, you know. So we have seen that ungrinded is much larger, around 200 nanometer, whereas grinded are much less, below 100 nanometer, which is now qualifying to be called as 100 nanomaterials, because for the material to be called nanomaterials, its dimension has to be less than 100 nanometer, and then we had gone into that regime, and it was verified this through this also. And also we had gone for SCM, FESCM, and FTI, the analysis also we have gone. And these are formal study we have gone for TL study to know the band gap. It's a wide band gap material. So the peak around 400 nanometers is the band edge luminescence. And there is a peak also at 532. This is the defect level luminescence. That is general in zinc oxide that is being found. So we found the similar behavior. Then we had gone for the results that we have shown here. That has been shown here. You can see these are these are results of photocatalysis of MB dye. When we go for the experiment, we used to give the nanoparticle into the dye solution, and we used to go for the stirring at zero light or dark condition to have a adsorption desorption equilibrium. Then after that half an hour, we used to take around centrifuge or a stagnation method for separating the nanoparticles. Then after the nanoparticle gets separated, we had gone for collecting them and gone for UV visible spectrophotometer study, absorption spectral study. And you can see exactly after half an hour, we started the light. At that point, we call it as a 0 minute light exposure. and the dye solution was like this at the was very deep, and you can see the absorption peak also was very high, 0 minute black color peak. You can see this is a typical absorption peak of methylene blue. So that was very high, you can see. Then we have got when we have increased the exposure time, every time we go for a interval of exposure time, then we need to switch off, then we have to collect the light sorry solution, go for separation of nanoparticle, then gone for this observation study. This way we continued, and this is a general procedure. And you can see we found that within 16 minutes we can completely decompose, which was also clear uh, from the observation study. So this was because it was a low cost experiment, and it was published in a very good journal of material science, materials in electronics, and it has been cited more than 20, I think, at this point of time. And now by observation study or by just visual also you can know, but to go for a deeper analysis you have to go for some other things like kinetic study. So what you have to do here, you have to find out the C by C0 ratio at different interval of time. C at any time, any instant of time, C0 stand for concentration at 0 time. This is by Bios-Lambert's, you can know that this is equal to A by A0. A stand for observance at any time of exposure, and A0 stand for observance of the dye solution at 0 exposure time. So because we are finding the observance, so their ratio simply give us the C by C0 ratio. And you can see initially this is 1 and it is gradually decreasing. And the you see the black one curve represent our grinded zinc oxide nanoparticles, and the Dugusa was showing much inferior result than our materials. And that was also reflected by a one has to go for a more detailed analysis called for that you have to go for plotting a graph between ln C0 by C and time. From C by C0 you can easily find out ln C0 by C, and when you plot this, then these scattered points give the actually experimental results, and the red lines are the fittings. You can see these fitting curves give the slope and these are the linear type of fittings. So these are called pseudo first order reaction, and the slope of this curve generally gives the reaction rate constant. This is the standard procedure for finding the quantifying the photocatalysis reaction constant. So the slope is very much high for our materials. You can see in compared to the Dugusa P25, which is the standard materials. Now, from that slope, we found that for P25 it is coming 0.06, whereas for our material it is coming 0.18. So this that means around 3 times enhancement of the reaction rate constant was found, whereas in ungrounded it was found to be a little bit less. Then we tried to go for comparing the how much has other people have shown in the world. Then we found that that ours is the highest in this, so it is really showing good result at that time. But the reviewer also asked, just make sure that there is no absorption, significant absorption in your materials. So we had gone for, so he suggested, reviewer suggested that you must to go for a test called scavenger based test. Scavenger are some chemicals that when you put into the solution, that will absorb the hydroxyl or other element or radical oxygen which are mostly used for this redox reaction, the scavenger actually absorb them. So if those things are coming because of the those redoxal or those active element, then scavenger will definitely create a big difference, and that was found to be there. There are two types of scavenger we had to use. He had suggested that one is EDTA and another is IPA. So we found that with the addition of scavenger, the reaction was reducing. So it is this confirmed that all the things that was coming was because of the photocatalysis activity only, not because of the adsorption process. So then we continue for other materials like methyl orange. You can see we got similar result. Then we had also done for other materials like macrolide greens, and then we switched to our to the UV light source also, and we found also good. In this case, we had not found that much significant result. You can see because zinc oxide is a wide band gap materials, and there was some decomposition, but it was not as high as UV light decomposition. But when we did the experiment with solar radiation, we got good result. Within 30 minutes, we got the decomposition, as you can see here, and the origin is obvious. Region I'll tell you, and here also we found that when we did the experiment with the actually you see with the visible light, and this is with the solar light, and we try to go for a comparison, and we try to find the region where in the normal visible light, artificial visible light, we didn't got good, but in the solar we got good. Then we try to compare the spectrum. I had actually spectrum spectrometer from another project of mine from a CRB. So I tried to see the spectrum, and I found that this B actually, B curve stand for the visible light, artificial visible light, whereas A stand for the sunlight. So the sunlight spectrum has significant amount of UV radiation, you see. Therefore, we got very good photocatalysis in the solar radiation. So that was also published. All detail about the publication I'll show you now next. And in the solar also we decompose other dyes, you can see. We have decomposed also this crystal violet. So this is okay. These are the publications related to the zinc oxide. So you can see the red lines are the very significant publications, you can see. And then coming to the titanium dioxide. In the titanium dioxide, we did the two types of experiment. Now I'll go fast in the my talk. Actually, I have almost given the basics. Now in titanium dioxide, we have gone for making the thin film also, and also powders. So in the thin film, we had gone a process called non-conventional sol-gel technique. We call it non-conventional because we started from actually powder of the same material. So generally, when you go for creating any nanomaterials for let's say titanium dioxide nanoparticles, then you have to go for titanium chloride and other type of chemicals. Or if you are going for zinc oxide nanoparticles, then you have to go for chemicals like precursors like zinc acetate or zinc nitrate, like that. But those precursors are very much hygroscopic in nature. So, and they easily you to get deteriorated. So, whereas these powders are very stable and their cost are almost similar. So, we started to do this type of experiment, starting from powder, going from the micron size powder. We gone for making it nano dimensional powder. One method was the grinding method. Then another method was the sol-gel method that we did. But dissolving oxide in any solvent was a challenging task. We tried for different things and we got this. This flow chart is showing that. And then after getting the sol, actually we just gone for dipping the sample and gone for the thin film preparation, or sometimes we caught it by Dr. Blade method. Sometimes we also doped it because in the sol-gel method you have an option for doping it or giving a impurity to it. So we have gone for giving the iron oxide type of materials to go for changing the band gap. Actually, iron oxide has a band gap of around 2 electron volt, whereas titanium dioxide has 3 electron volt. 3 electron volt goes to UV region, whereas 2 electron volt goes to visible. And visible light sources are cost effective, and also solar radiation has significant of visible radiation. Doping or tailoring the band gap of the materials, that is called band gap engineering. So we had gone for adding those type of impurities, and these are the materials. And first we did the experiment with the slides, but we had not got the success. Then we directly caught onto the beaker and we had gone for the experiment and we really got the success. Okay, before that, in the slides, we had gone for doing these conventional studies like XRD or crystalline size determination. These are the routine work that we did, and we found very small crystalline size also. You can see these are the routine type of works for all type of material that we have grown, and we had gone for the other conventional studies like FASM and so. And we found that those are really coming in the nano dimension. So, what I'd say, we had gone for converting the micron size into nano size by just adopting this process only. And we did the experiment, and we got that in nano size, that is really showing good result. And the cause is very much obvious, because in nano dimension, the surface area is very large. So large number of dye molecule adsorb there, and they get splitted out by photocatalysis. So that was being proved in our case. And we had gone for decomposing various materials, and here you can see raw powder. The last one is showing much less, whereas the material processed material showing much higher reaction rate constant. And we had also gone for heat treatment at different temperature. Then we found differences result. This is for optimization things, and these are being also published. Different type of dye we have decomposed. Now, now going for the this mixed material. This is called zinc orthotitanate. If you mix the material 2 molar zinc oxide and 1 molar weight of titanium dioxide, then you can create such type of more sophisticated materials, where you can tailor the lifetime of the materials, recommendation of the lifetime and other things. And that can really enhance the performance, and that was being found actually. I'll show you this, but just see the method. This is the solid state reaction method that we have adopted. Probably many of you know. In the solid state reaction, you have to grind the things, the materials in wet medium, like acetone also. Then you have to go for high heating at very high temperature, like we had taken 950 degree centigrade. Then we had gone for the XRD of the material. Then we found significant good amount of zinc orthotitanate peaks, and but residual zinc oxide, titanium dioxide also we are found in our materials. That is, you can see, generally it's very difficult to really go for 100% conversion of the materials. So, but significant zinc oxide was found by this peak, and then we had gone for the particle analysis, and those were coming within the 50 to 60 nanometer, we found, and that was being already confirmed through TEM. Then we had gone for other study like diffuse reflectance spectroscopy to know the band edge absorption, and it was coming similar because both of the material has large band gap. And we had gone the PL study also, but in this case the defect was found to be more. So that means the defect absorption was there, eh, and that was found to be more useful in our visible photocatalysis. I'll show you later. Now, when we did the experiment with UV light, we found that for both of the constituents, the compound was showing much higher, and we tried to find out the reason behind this, and we found that the one of the biggest reason for the increase of the lifetime of the excited carriers. Generally, lifetime used to increases. So electron hole pair used to stay in separated way in much longer time. So the reaction takes place for longer time, and it shows the faster means better result. And here we had shown this result, you can see, and also we had gone for comparison with 325. Then we had gone for the recyclability study. Again, the reviewer had asked us to go for recycling study, how much times it can be recycled, and then we found the material can be up to 5 cycles. That was almost similar result we found, and that we have reported in one of our publications. And in that we found that this material can show the much higher, 6 times higher than that of P25, and we had compared with different other materials. Okay, so that was published in Jalcom actually. So we had gone for visible light. This is the spectrum I told you. Visible also we got good result, and this the second one I'm telling about, Jalcom paper. So that is also highly cited paper now. And then just briefly, probably I'll just before winding up, I'll tell you about sometimes you can see I used to develop the reactor myself, and I'll be happy if anybody is approaching me, then I can help them or can give the necessary support in developing the systems. One of the systems that I developed is like cost-effective laser observance spectroscopy system for evaluation of photocatalytic activity. Motivation was that you see for finding the reactant reaction constant, you must have to go for observance study, and for observance you must have to go for spectrophotometer, which has the cost of 5 lakhs to 25 lakhs. Earlier I was not getting access to the such type of system very often in the beginning step. So you have to test many times. So I tried to go for thinking some new cost-effective systems. So what I found is that you see the observance of this methylene blue, it is coming at around 650. That is exactly matching to the helium neon laser or any other red LED. So so I try to go for a very simple setup, and the setup I'll show you. Sorry, so I don't know. Just let me see. This is a setup actually. In one side I had given a lux meter, and in one side I had given the actually the laser source, and in the middle I had kept the sample actually. It was a very simple setup, and I can easily measure the transmittance, and from the transmittance I can easily find out the observance, and that is I did actually. And I verified with the conventional one also, and I found it is coming similar result. So I tested different type of materials with this method, and and uh, this system was very less cost actually instrument. uh, Helium neon was a little bit higher cost that I used, so it was coming within 25,000. But later I changed the configuration and it is also much less. Okay, anyway, so these are the various publications, and now I'm at the end. Before concluding, I must acknowledge my PhD scholars. Udasis, Ligina, Prabhakar, Rajashree, Otol, and Chandrakanta. Uh, Actually, this slide is is much older, but they are now in different position now. So, but I must also thanks the funding agency SCRB and Nano Mission, Government of India, DST. Also, I'll acknowledge my collaborators at Niger, PK Sahu and of Niger, and the Pradhan of IIT Kharagpur. These are the students. They are some of them have worked in this field. Three of them has worked in this field, and some others has in different other field. I'll show you different field that I'm working in. This is the first group and second group. All those has been awarded. These are third group students who are continuing now. So uh, all of the students are now well placed, as sir was saying about my citations. All of them are well placed in different organizations. Uh, Many of them are in government of Odisha or government of India actually. And also during my MTech, I supervised a number of students, international students. Like 1 and 3 are the students from Europe, and they are well placed in the Germany itself. And one student from VIT has visited in a semester abroad program when I was at Maximum Institute, and he is currently at USA. So now just I have now already covered my topic. Just to have a look to the research area, I'm working in different things. The first one is actually design development of CW, nanosecond, picosecond, femtosecond lasers, solid state lasers. Then shaping diagnostic system of lasers, nonlinear optical material devices, laser material processing and spectroscopy, optoelectronics, mostly photocatalysis, and recently I started. Actually, when you are going the advanced material, you must have to go for applications, and I had gone for applications actually. And last but not least, agrophysics is one of the latest work that I had started actually, particularly climate control agriculture. For that, very low cost equipments I am now developing. For example, one example I can say, solar based climate controlling systems, through which you can go for mushroom farming throughout the year. Now those type of things are getting done by the rich farmers, those who are spending crore of rupees in establishing the setup. But for giving a direct benefit to the society, I am now developing the systems which cost 5,000 to 10,000 to 20,000, within that range, and one can really use those. Talk, I'll definitely go for um, telling those things. So they are my motivation is to go for converting waste to wealth, and going for the green technology. So with this, I'd like to thank you all for your kind attention. Thank you.
Thank you, sir. Thanks for your enlightened talk, sir. So
Sir.
participants, if you have any queries, please you can ask your doubt to the expert. Otherwise, you can text your questions in the chat box.
Whether students, so participants have understood the content, I believe,
Yes,
yes.
sir.
Uh, okay, sir. Thanks, uh, Dhavan. Okay.
Dear
Um,
Professor, good morning,
yes.
Professor. I have one question, Professor.
Yes.
Am I audible?
Yes. You are audible.
Yes, sir, sir. Professor, you mentioned the zinc oxide having 60 milli electron volt. That is the large excitant binding energy at room
Yeah.
temperature, right?
Yeah.
Yes, sir. So how it will be support for photocatalysis activity? Whether it will be whether this value will be changes with respect to the particle size?
No, actually, let me tell you. Excitons are the actually when there is a electron hole pair creation due to absorption of photons, they used to have a actually attractive bonding between them. So they behaves like a single particle. So that is called as a quasi particles. That is called as exciton. So because of the excitation, so there is a means they have a tendency to go for recombination also. Okay. So for some
Yes, sir.
other, let's say photodiode and other applications, it's a very good type of because this exciton is when the exciton bond energy is more, then there is more recombination probability, and faster will be the process of recombination. Lifetime will be smaller. So in that is of course little bit detrimental, but because it's a direct band gap, absorption probability is more, so there is a trade-off actually. So this excitation binding energy for this application is not that much good, but for other photodiode and other applications it is good. So when we go for combining this material with titanium dioxide, then the lifetime increased, because in that case the binding energy is reduced.
Okay, okay, Professor. Thank you. One more question.
Sure.
So and also you have shown the so the zinc oxide having the 16 minutes irradiation, you have getting the maximum dye degradation, right, Professor?
Yeah, yeah, yeah.
This is the great achievement. This how is it possible, and what are the parameters begin this, particularly in terms of the properties of material?
Yeah. uh, Particularly, there are a couple of factors here. Uh, the in this case, you see, particularly we compared our material with the P25. You have seen P25 actually is a titanium dioxide, is a indirect band gap materials. Zinc oxide is a direct band gap material, so its observance is more. So in our case, the observance of the material was found to be much higher. So that is the biggest reason of means big reason for this good behavior.
Okay, Professor.
Mm.
Whether the surface area, whether it will be influenced, Professor?
Pardon?
Surface area of the zinc oxide, whether influence
Yeah,
the
yeah.
photocatalytic activity.
We had gone for surface BET studies. We have gone for 800 meter square per gram. We had found actually. I had not shown here in this case. BET study we had gone
Okay,
for. Mm.
okay, Professor. Thank you so
Ah,
much.
welcome. Also, let me tell you, I don't know how many type of students are, so participants are there. Particularly, uh, if there are new faculty, for them, I have a advice. It's very difficult to start a research when you are in the beginning stage. So in that case, definitely you have to go for means cost-effective approach that is within your reach. And you see, when I was at IITs or in Germany, I was associated with the big laboratories and huge infrastructures. But when I joined a college like KIT University, I landed nowhere almost. So At that time, that I changed my topic actually at that this because my MTech was solid state materials at IIT Delhi. So that knowledge I utilized to grow the materials, and I switched to the photocatalysis application rather than going into the my core research of laser. Later on, I got the project on laser also. Then I switched to that. I continued that, but what I mean to say that you may not have to stick to your core field. Okay, when you have a research knowledge, just I believe research is just knowledge means just learning a cooking, and cooking means you can cook any type of things if you have basic idea. Similarly, so I utilize that thing in my research field, and that's why uh, you can see my research publications and citations are good. So I advise you should of a similar thing. Anyway, any other question, mm, or maybe you can give me message or mail my mail. You can take a screenshot or give me WhatsApp message. Particularly, I am comfortable with WhatsApp. Uh, you can take the screenshot or take the uh, you can give me WhatsApp or email. Okay, uh, you can get all details from my university's webpage also. Okay, anything else? If not, maybe we can wind up here.
Yes, sir. Thank you, sir. Thanks for your session, sir.
Yes.
Thanks, Karthik, for your question. Is there any questions from audience, or shall we will wind up the session?
Yeah,
We will move to the next
you
session.
can also give me mail or WhatsApp anytime. Okay.
Okay, sir. Okay.
Yeah.
Okay, sir.
So then,
Okay, then. Thank you, sir.
yeah, thank you all the participants once again, and my sincere and thanks and gratitude to the organizers. Thank you all. Bye. Have a nice day.
Right, sir. Thank you, sir. Okay, thank you, sir. Dear participant, shortly the second speaker will join in this link. Please wait for 5 minutes for him. He will join within a 5 to 10 minutes.
Participants, please be on the meeting. சொல்லுமா The second session will be started soon. The speaker is going to be joined, so please be on the meeting.
Sakthivel, sir. Shall we start, sir? Dear participant, he has already joined in the link. Just wait for 5 minutes. Sir, good morning. Am I audible?
Yes, sir. You're audible.
But I can't hear your voice.
Now, can
Hello?
you hear my voice?
Yes, I can hear your voice.
Fine,
So,
sir.
sir, shall we start now?
Yeah, sure. Let's
Okay,
start.
thank you.
Sir, let me welcome you for this session. Then you
Yes.
can share this.
Yeah, sure, sir. Sure.
A very good morning to all the participants. Today is the third day. We have completed session one, and this is the session two. Today we have Dr. Kogularasu Sakthivel, professor in Cheng University, Taiwan. Sir, I extend my hearty welcome to you, sir. Dr. Kogularasu Sakthivel has completed his undergraduate and postgraduate in chemistry from Bishop People College, Trichy. Completed his doctoral degree in chemistry from National Taipei University of Technology, Taiwan, in the year of 2019. He started his career in MRF Limited India in R&D lab. Later, he served as postdoctoral researcher, renewable energy and applied photonics lab, National Cheng University, Taiwan. Currently working as professor in Cheng University, Taiwan. His field of interest, electrochemical sensors and biosensors, photoelectrochemistry, multi-dimensional layered nanomaterials, functional inorganic materials, sustainable synthesis, environmental chemistry, energy storage devices, analytical chemistry. He has memberships in the prestigious societies such as American Chemical Society, Royal Society of Chemistry, Electrochemical Society, the Physical Society of Taiwan, Indian Institute of Chemical Engineers. Also acted as guest editor in peer-reviewed journals, reviewed about 150 ACA articles such as ACS, RSC, elsewhere, Springer, etc. And he is a member of Model United Nations, and also he is a country representative of JITC, Global International Teen Conference, to select the Global Teen Hero. He has published more than 50 peer-reviewed journals with a high impact factor. His expertise in material characterization, such as NMR, FSM, HRTM, XRD, BET, and XPS. Also, he is skilled in separating and purifying the synthesized organic compounds by high pressure liquid chromatography, expertise in electrochemical studies, chromatography techniques, conductivity titration, etc. Really, we honored to have you today, sir, in the session two. Sir, welcome you, sir. The session is yours, sir.
Thank you very much, sir. Thank you very much for the nice introduction, sir. And yeah, and I'm glad to be in this event. Actually, it's my pleasure to be in this wonderful event in one of the finest institutions in Tamil Nadu. And today I have chosen a title to deliver a talk. It is on developing next generation glucose biosensors. But this talk is not only for glucose biosensors. The people who are working in biosensors can also adapt these kind of techniques to develop it into like moving it towards the next generation. And before starting, I wish to introduce the institution which I come from. Currently, I'm working in Center for Environmental Toxin and Emerging Contaminant Research. Shortly, we call it as Center. And this is established in 1999 and it is the first dioxin lab in Taiwan. And in 2018, after the MOE, Ministry of Education subsidies, the center is grown and they renamed it as Center for Environmental Toxin and the center. And in 2023, it is integrated with the university, Cheng University, and we have all the international standard license which are issued in Taiwan. And we have a collaboration with international giants and as well as the world contributions with almost we cover all over the world. We are doing samplings, testings, food samples, drug samples, and even the abusive drugs and this center involved in detecting the abusive drugs in. So my screen is full screen mode, right? So could you please confirm, sir?
It is not in the full screen mode now.
Uh-oh.
It is moving now, but it is not in the full screen mode. You come through the entire screen.
Can you see now, sir?
No, sir, it is coming as a PowerPoint presentation mode only. So you can stop sharing the screen,
Uh-huh.
then come with the full screen mode. Again, share with the full screen mode.
Now is that clear, sir?
Yes, now it is full screen mode.
Yeah. Thank you, sir. Thank you. Yeah, let me continue now. So here are some international laboratory analytical technique comparison, which we have done for the several years, and, and we have selected as the top ranks of excellent sensing under a center in Taiwan. And here are our collaborators, and also it is an honor to work with NASA and many good universities in the US. And so, yeah, we are looking for collaborations very soon to do with India. And here are the things we do: integrated analysis method for tracing air pollution. We have the sample collectors all over Taiwan, and we detect and we are issuing the reports to the government, Taiwan government, and diagnosing the efficiency of pollution control devices. So when we sense, when we detect the pollutions, like near the harbors or anywhere, with certain kinds of control devices like detectors, and as well as uh, the collectors, we prepare the devices and we are giving it to the government. And also we do the health risk assessment, and also we involved in investigations on soil and groundwater pollution. And we have taken several steps, and also we have working on seawater pollution control, and we focused on net zero emission goals as well. And here are the cutting edge equipments which are in our center. Yes, let's get into the topic. So actually, we should understand why the next generation biosensors are necessary for glucose. Because I think in the recent days, in almost all over the world, we are using a modern biosensors, like we are using the strips and a small sensors, like small compatible devices in our hands to detect diabetes. But the reason for moving to the next generation is because before we have the diagnosed and undiagnosed, but the American Heart Association as well as the American Diabetes Association said that the number of adults with pre-diabetes is too high recently. So, which means it is very close to diabetes, but it is in between the normal and diabetes. So, we should have the devices to sense um, to the lower detection limits, because most of the biosensors can only sense when the people have diabetes, but when the glucose level is lesser than the diabetes level, which means too lesser than the diabetes level, that devices are not capable of sensing it. So it is necessary to develop the next generation biosensors to sense with the low detection limits. And it has a good history, like from the first generation of the sensors. Initially they started with oxygen biosensors, that is by sensing the oxygen in our blood, we sense the amount of glucose which is present. So that is how initially the glucose was sensed. The next one was immunosensors, like using the enzymes to coat on the surface to sense the glucose. But when you use the living organisms like enzymes on a device, of course the repeatability is very difficult. The repeatability is not easy to make it every time when you, because it is dependent on the temperature and the weather. So when it changes, the enzyme's reactivity changes, so that it cannot be gone. So in the third generation, it is like they started using the strips, the test strips, which we are currently using now, and still it is moved further by adapting it with nanoparticles. So we call it as nano biosensors, which started as the fifth generation. Currently we are using the fifth generation is like a wearable, because glucose sensing is moved like sensing with the microneedles, even the tooth enable sensors, which we can place it on our tooth and we can sense like how much food we eat. It can calculate like how much glucose we intake. And even it is currently many people are using like epidermal tattoo sensors. So the tattoos can sense the sweat, and it can diagnose the sugar level on many things in our body. It depends. So currently we are in the fifth generation of biosensors. That is the point now. And before that, many conventional methods were used, like liquid, the chromatographic techniques like liquid and gas, and mass spectroscopy and IR spectroscopy. Of course, this is more precise, but this instrument is too big and it is little hard. It is fine, but when we use it for pollutant or toxic substances, then it is fine. But sensing for a glucose, sensing a glucose, that must be real time. So that is real time to help the patient. So when it comes to biological stuffs, it is always better to go with the real time sensors, real time detectors. And when it comes to electrochemical method, it don't take much time because it works on real time. The redox of like glucose to gluconic acid, the oxidation instantly gives the signals, and from that signal we can sense like how much glucose is in our body, in the blood, urine as well. So here we can see um, it comes with just three segments. The first one is the receptor, the analyte, the nanomaterial which we use, and the device, and the detectors. So the first, the receptor means, is a kind of an electrode which is adapted with the nanomaterials. And when the analyte, so here it is a glucose, and if you are using it in a different field, so any other pollutant or toxin, any kind of analyte touches the nanomaterial, the reduction, the redox reaction happens, and that will be processed in any kind of transducer, like it may be a potentiometry, amperometry, voltammetry, impedancemetry, or conductometry, any type of uh, transducer which is suitable for our reaction can be used. So this will process the signal, and it reads the signal and send it to the detector in a readable way, and we can transfer it to the cloud or where the data should be saved. So in this method, we are planning to use, so this is a kind of mechanism. Actually, this is a non-enzymatic. As I said before, when we use the enzymes, the repeatability and reproducibility is a little difficult. So that we are currently going with non-enzymatic studies. So this is how the electrode looks like, and the nanoparticles are designed on the electrode, which means the strip. And so when the glucose in the blood is oxidized into gluconolactone, the electrode, that electrode reduction will happens on the material coated on the electrode. So this yeah, electro reduction process gives the signals, and which is received to the electrode, and this is sent to the transducer, and finally it is received through the detector, which we are get as a data. So this mechanism, this mechanism is simple, and just by the oxidation and the reduction, we get the signals from the electrode. So this is in on real time. So that mechanism is a basic one. So when it compares with the conventional methods, there are some difficulties because it is less cost effective, which means we have to spend a lot for calibrating the big devices. And of course, it is not slow, but it takes time for the calibration and high maintenance. But when it comes to electrochemical sensors, it's cost effective because it's like a strip. Or when we use the glucose biosensors, we just use the strip and it is a one-time usable, so we can repeatedly use. So it is user-friendly and highly selective, fast and sensitive. So let's come to the scientific part of this work. This is how the electrode is prepared. So in this work, for developing the next generation glucose biosensors, we have used nickel tungstate. So here is the synthesized method. We use the hydrothermal method with a low temperature synthesis of 180 degrees Celsius for 12 hours. As initial substances, we have taken nickel nitrate and sodium tungstate to prepare nickel tungstate nanoparticles. The reason for choosing this material is, of course, we know that the tungstate is more stable and the nickel is more conductive. So um, the synergetic effect of this material is renowned, so we have used it for this kind of glucose biosensors. And this is how we prepared. First, we make it as an homogeneous solution and we synthesize through the hydrothermal technique. After the material, after the hydrothermal synthesis, the precipitates are collected and it is calcined at 600 degrees Celsius for 4 hours to remove all the impurities from the nanomaterials. Then it was again sonicated because there must be some like clumsy particles, agglomeration or aggregation in that nanoparticle, so that after sonication it is dispersed into that to make it as a homogeneous thing, and we fabricated the electrode on screen printed carbon electrode. So here we have seen the final result. This is the thing we are going to use as a strip for sensing glucose. So of course, when we prepare any material, checking the property is the first thing. So we went for the structural properties. So when we checked, it is as we expected. We got the monoclinic structure of nickel tungstate, and it is proven by the X-ray diffraction patterns. And this is how the crystal structure looks. And the morphological properties, we have examined it through TEM, transition electron microscope, and it is the lattice fringes are all came as expected, like a nanomaterial with the D-spacing. And now we are testing it for calibrating it with sensing the real glucose. In figure A, you can see the green one is a bare, without any glucose. This is the result. And when the nickel tungstate is coated and the glucose is tested, of course we can see the higher folds of current. So the green is for the normal bare, which means without the substance, and when it is coated with our nickel tungstate, then it gives a higher peak, which means higher sensitivity. So we have used it, and the reduction and oxidation currents are mentioned graphically for more understanding in B. So here we proved that this material, which is nickel tungstate we have prepared, is capable of sensing glucose. Of course, it is very necessary because it must be increased gradually. Like when there is a sequential addition of glucose, and the current must be increased gradually. There should not be any change in that sequence. So that we have tested like 0.01 micromolar to 29794 micromolar. Until that, there is no change in the sequential order, which means we can use this material to sense glucose in this linear range. So we can use it as a sensor to sense from 0.01 micromolar to 279.4 micromolar. So here is the graph we have plotted, and we tested in the real world samples like bovine albumin serum, because we cannot use the sensor directly um, with the human blood because of few things here, and but we have used urine samples to sense glucose, uh, and we have gotten the results through the LSV methods, which are displayed in C and D. So next move to this is why we call it as a next generation, moving to the next generation, because you may see here, it is a card-like biosensor, because currently we are using it as a compatible device, but these kind of sensors, like when it is a kind of potentiostat, in figure A you can see it is a kind of potentiostat for one-time use. And here we have NFC, which means of course you know that like we used to pay the payment like Apple Pay or something. So here we have the near field communication like NFC here. So when you place your phone on the top and you drop a blood or urine sample here, you can immediately get the results without any devices, external devices. So that, of course, in the recent days, everyone is having a mobile phone with them. So we can use it in our wallet, and we can use it directly, like when we can place it on a table. The card is on a table, and we have to place our phone on that card, and when a drop of analyte is placed here, we can immediately sense how much glucose is in our body, and also that will be transmitted. When it is detected, it will be immediately transmitted to the database, and of course it will receive the patient in a readable way. I mean, if it is glucose, then it is fine. But if it is you're sensing a tumor biomarker, cardiovascular disease biomarkers, then of course that must be not readable by the patient. So this can read, and the database will be made, and it will be sent to the patients in a very readable way. And of course, that is also sent to the doctor's desk for his next things. And so if it is yeah, here we have tested it with our prepared the credit card type glucose biosensor, so that the thing shows on the left side is pretty old. Maybe this maybe we are trying to apply for the patent. Maybe if it is successful in future, the glucose sensor may be changed like the thing which I shown on the right side. So if the glucose biosensor or any kind of biosensor is moved, of course that must be integrated with our mobile phone for better compatibility. Yeah, thank you.
Sir, thank you, sir.
Yeah, thank you.
Thanks for your enlightened lecture. Participants, if you have any queries, please text in the chat box, or you can unmute yourself. You can ask me. Question, sir, I already put out the posters in the WhatsApp group. You can see the expert details in this WhatsApp group also. So, any other questions? So, can you share your email ID with the participants, sir?
Yeah, sure, sir. Sure. It is. It is here.
The hand. I don't know who. Hand raise one more.
Sorry, sir. Could you please say it again?
Okay. Yes, sir. You can.
Yeah. Thank you, sir. Thank you.
Thank you, sir. A formal vote of thanks will be there.
Yeah.
Yes, please.
It's my privilege to deliver the vote of thanks for the third International Faculty Development Program on Advanced Functional Materials, Energy, Environment, and Sustainable Development, organized by Department of Physics in association with the Department of Mechanical Engineering, SRM TRK Engineering College, Trichy. First of all, I would like to thank the management, SRM Group of Institution, Trichy and Chennai campus for giving this opportunity to organize this type of events regularly. I would like to extend my thanks to the today's resource person, Dr. Kogularasu Sakthivel, Assistant Professor, Bio-Electrochemical Sensing Technology, Center for Environmental Toxin and Emerging Contaminate Research, Cheng University, Taiwan, on the topic developing next generation glucose biosensors. I also thank the organizing team for this FDP program. Finally, I thank the participants, research scholars, faculties in and around India and from the other countries who actively participated throughout the program, and they made this event as a grand success. Once again, I convey my thanks to the all. Thank you, sir.
Yes, sir. We close the session, sir. Will posted in a few minutes. Please wait the participants. Afternoon, we have two sections today. One is the international seminar. Another one is a national workshop. So that techniques will tell about the electromagnetic shielding as well as the SEM. So the one person from colleges will be delivering about the SEM techniques. So thanks for your participation. The feedback link will be shared shortly. Ms. Kalaivane, I have discussed your question with the expert person. He will answer you soon in the chat box. Thank you. Participants are requested to fill the feedback form at the earliest.